Oh, hello. Hello, good morning. I guess you might be wondering how you got there and why is this rabbit-shaped Arduino talking to me. First of all, there's no Arduino in there. I run on a Siemens 1214 AC/DC relay PLC and a hamster in a wheel. And second, have you heard about parallax mapping? Some of you might know what parallax mapping is, so I will explain it to you the same way someone makes a video essay about their backrooms. Parallax, from Latin parallaxis, is known as the effect of displacement on a surface. Take for example this picture of my cat. It represents the surface displacement on the floor from its current position to a lower point due to my cat's massively fat ass, hence this image is parallax. Okay, but what is parallax mapping? Parallax mapping was introduced by Tomomichi Kaneko in 2001, open bracket 1 close bracket. This technique became very useful to render highly detailed 3D surfaces without the need of a high polygon density, and it's still used very commonly now, which brings up the question, what actually is parallax mapping? For that, we have to go back to 1963 with the release of Sketchpad, the first 3D model. Do you get what's the problem now? Okay, let's be serious. Partially. Parallax is basically displacing a graphic relative to your point of view in a way that it simulates depth. In 2D, people can make use of parallax scrolling, which displaces graphics faster or slower depending on how far from the camera these are. In 3D, you can do parallax mapping, which uses a texture that represents the height of the surface details. Parallax mapping itself consists of a single shape, which looks okay from up, but it's terrible when looked at from the side. That's because it was 2001 and well, yeah, it was 2001. So the currently used method owns the name of parallax occlusion mapping, which makes it so bumps that are higher than what is being rendered behind them get occluded, instead of making this weird gradient. There are various ways to calculate this, but the most common one is parallax rendered by layers. By the way, I want to give big props to world creators that use parallax shaders instead of first shaders for their rugs, because it runs so much better. If you wonder what causes this performance impact and this repulsion towards this shader among many people, it's just one word: overdraw. Take it simply as, you draw a mesh on the screen, then another one on the same screen, then another, and so on and so on and on. That's overdraw, and GPUs are clearly not accelerated for this. Parallax mapping reduces this cost significantly by rendering the layers and calculating everything else on the same pixel shader. Go to your project and create a new unlit shader as always. We have to calculate some things before we start doing stuff. This will be a very common thing when making shaders. Our app data structure will contain the vertex position, UV coordinates, the normal as a float 3 and the tangent as a float 4. The vertex to fragment structure will output the vertex screen position. The UV coordinates, the wall space normal, tangent and bitangent, the wall position and our view direction, all of this as a float 3. And yeah, well, the 4 coordinates but that's a Unity thing. Going to the vertex shader, we start with the wall position, which is a multiplication between the object to world matrix and the updated vertex position. The view direction will be underscore wall space camera pause minus the wall position we calculated. The wall space normal will either be the multiplication between the object to world matrix with update as normal or update as normal with the wall to object matrix, depending on a keyword called unity underscore assume underscore uniform scaling. The wall space tangent is also the multiplication between the object to wall matrix and the XYZ axis of updated tangent. Lastly, the bitangent is known to be the parallel axis between the normal and the tangent. So we get the cross product between the normalized wall space normal and tangent, then multiply that by the W value of the updated tangent, and lastly multiply it by the W value of unity underscore wall transform params. You see that I normalized the normal and tangent there, but kept them unnormalized for themselves. That's because in order to get good quality normals, you need to normalize them per pixel, not per vertex, because the rasterizer interpolates linearly and normalizer and a vector turns it circular. There's this thing where you can put a shader on the skybox, get the normal normalized on the vertex shader, then another one normalized on the fragment shader. And if you get the difference between both, you will see a real shape of the skybox. In this case, it's an icosphere. Fancy, right? And so when you finally get to the fragment shader, you can normalize the view direction, the normal and the tangent. Let's set up the parallax function. You can do parallax in two spaces, as far as I know, wall space and UV space, also known as tangent space. The most common space is UV space because, well, that's where people usually map a texture. But since they barely have any difference when it comes to calculating the parallax occlusion, I don't mind explaining you wall space parallax too. So first off, our necessary vectors. Parallax requires two vectors, one for the coordinates you want to map your parallax in, and then a vector that will offset these coordinates to give the effect of depth. So in case of wall space parallax, the coordinates will be the wall position. The parallax offset requires some calculations. This vector can just be the view direction, which will be correct, but you might notice a big issue. The coordinates are being displaced as a sphere instead of your normal. The solution to this is dividing the offset by the axis that is parallel to the normal. So if you're rendering a plane that faces up like a carpet, you only need to divide the offset by its y-axis, which unwraps it from the sphere shape to a plane. That's just a gradient that is 1 at the center of the offset vector and fades out to 0 to the further away it is from it. The same can be done with any other normal direction, but what if you want to adapt it for an arbitrary direction? For that, you have to get the dot product between the offset vector, which is the b direction, and the wall normal. Also, an interesting fact, the value is also used to get the rim and Fresnel. Pretty bonkers, right? And so these are the vectors for wall space parallax mapping. If you want to use these vectors, you can jump to this time. Okay, are they gone? Now I will explain how UV space parallax mapping is done. The vectors for this one are float 2, and the coordinates are the UV coordinates of your mesh. Very important, this only works with the first UV coordinates of your texture. If you use any other UV coordinates and they're scaled or rotated, parallax mapping won't work correctly. Same goes for normal mapping, by the way. The offset is also the view direction, but rotated to UV space. So you have to create a float tree for that vector, which is a multiplication between a 3x3 float matrix, where the first value is the x direction of the UVs, so the tangent, the second value is the y direction of the UVs, so the bitangent, and lastly, the up direction of the UVs, which is the normal. Then the second value of the multiplication is the view direction. Remember that you need to divide the vector by a gradient to correct the offset into a plane. In this case it's easy, as I said before, since it's rotated towards the UV coordinates, which is static, unlike wall space, the vector only needs to be divided by the up axis, which is z in this case, since the x and y are the UV coordinates already. Now with these vectors, let's add a float property for the height of the parallax effect. The unit of this value is a meter, so 0.05 will be 5 centimeters. To read these calculations, you can multiply the offset by this value directly. And if you want the parallax effect to happen inside the surface instead of outside, subtract the coordinates by that offset. Then create a uniform integer that represents the amount of iterations you're going to do. And optionally, you can create a separate function to sample or calculate the height map. Its input will be the parallax coordinates. If it's in wall space, it's a float 3, and if it's in UV space, it's a float 2. And the return value will be the parallax height. It's usually a black to white texture, but it can be any formula. Now we can start doing stuff. First, simple parallax mapping. That's the one I mentioned before as the first method, when you don't need to iterate, but as a result it's only effective if it's in from up. The formula is the parallax coordinates plus the offset multiplied by the height map, with its vector being the same parallax coordinates. That's how it looks. Something you can do to reduce the imperfections is to decrease the offset's intensity the more you look at it sideways. This value can be calculated as the dot product between the normal and the view direction. This method is good for parallax effects that are not very intense and are not very important, so it's like a small detail to put on your materials. Next we have a simple type of parallax occlusion mapping. It renders as layers, just like first shaders, but without the cost of massive overdraw. Start at the highest point of your parallax coordinates, so the coordinates plus the offset. Then what we are going to do is moving the coordinates downwards and subtracting the map by the height it has traveled, giving us the remaining height. If that remaining height is lower or equal to 0, it means it's occluded, otherwise the coordinates will be shifted by the offset. First, we get the face as a float, which will represent the height is traveled. It will start at 1 and then at 0. I need to hydrate. Robots need water too. Have you seen the new Minecraft movie trailer? Then get the height delta as a float, which represents the height between every iteration. It will be -1 divided by the number of iterations as a float. -1 because it's going to move downwards. We also get the offset delta, which shifts the coordinates by every iteration, that is the negative offset divided by the number of iterations as a float. Now create a for loop with the number of iterations. Inside it, sample the parallax map as a float using the coordinates, then subtracted by the phase. If this value is lower than 0, sum the coordinates by the offset delta and the phase by the height delta. This is how that looks. Although you can see the layers from the sides, it's a cleaner effect and it's a good method for starters. Next one is an addition to the previous one, so it's more of an extra for the first one. It starts as the previous function, with another loop after the main one, moving the layers upwards instead of downwards. This second loop gives more detail to the layers. The offset delta and the height delta will be negated to make them positive and divided by the number of iterations again. Inside the loop, sample the height map again, subtract it by the phase, then if the value is higher than 0, sum the coordinates by the offset delta and the phase by the phase delta. Now you can have n squared layers with only 2n iterations, where n is the number of iterations you set, at the cost of still having the first loop's layers if seen sideways. This next method is one of my favorites, binary search. Or if you want to sound fancy, binary search parallax occlusion mapping. This algorithm finds the point where a binary value switches to another one. It works as follows. You start from the middle. If at this point the binary value is false, it means that you should travel backwards. If it's true, travel forward. The travel distance is halved by every step, so every iteration is more precise. The number of steps you need to take for a binary search should be the binary logarithm of the sample count, which is the power you raise 2 to get this number. Our case is a bit different though. The binary search is performed to find the point at the surface. We start at the middle too. If the height map is lower than the current height, the next step will be downwards, otherwise it will be upwards. We start with the height delta as a half and the offset delta as a half offset. Then add this offset delta to the coordinates, placing it on the middle. The phase will start as half too. Create a for loop and inside sample the height map, then subtract it by the phase. Then get the sign of this value. Sign returns -1 if the value is negative and 1 if it's positive. Before moving the coordinates, multiply the deltas by half. And finally, sum the offset and phase by the respective deltas multiplied by that sign. This will displace the phase and coordinates towards their respective direction. This is the result. Pretty fancy and optimal. Now, there might be the case where you want to make the layers less visible, so you want to map the effect from your view, not the surface. That's where Raymarching comes up. Raymarching consists of repeatedly moving a ray towards a direction to find a shape, which is similar to ray tracing or ray casting, but made for arbitrary shapes. This function will start at the top too. Then every iteration it will shift by the height reduced by the number of iterations. The offset delta will be the offset divided by the iteration number as a float, and the height delta will be 1 divided by the iteration number as a float. The phase will start as 1. Now create a for loop and sample the height map minus the phase. The coordinates will be added to the offset delta multiplied by the value, and then sum the phase by the value. And it's simply that. This is how it looks. The layers are not noticeable anymore because instead of moving layer by layer, it wrapped the coordinates around the height. These are the different parallax mapping methods I know of, and after doing that you might want to give actual effects to this. And for that you need to extract the wall space normal of the parallax effect. Of course, you can have a separate texture that contains the normal map for the height map. I actually recommend you do it because it's more efficient, but in case you're not mapping a texture or you don't have a normal map for that effect, you can simply use a formula. This method shifts the map by 1 of each axis, then calculates the difference between the shifted height and the current height. The more intense the difference is, the more it's facing towards its axis. You will have to create a property or variable that represents how far will the map shift. It's usually called epsilon. This value will depend on the detail you want to extract from the map. If it's lower, it will have a more detailed normal. If it's higher, you will have a smoother normal. Now sample the parallax map on its current coordinates and we can start now. For wall space parallax, you have to get the map shifted to the x-axis, to the y-axis and to the z-axis. Then create a float tree for its wall space normal, which will be the normalized vector of these three results in their respective order, then subtracted by the current parallax map. For UV space parallax, also get the map shifted by the x and y axis. After that, normalize that vector and rotate it back to wall space by multiplying it by the tangent matrix as we did at the start, but this time in the opposite order, so multiply this vector by the matrix. You now have the normal. With this you can properly calculate the lighting of the surface with parallax mapping. This is where the basics of parallax mapping end. Let me show you now some cool things you can do with it. Starting with rock shader. You have probably seen these rocks on some beer chat walls. You can distinguish them from first shaders by seeing if they don't clip on the edges, or if they don't take away your frames when you approach them. I recommend you do this in wall space because that can be helpful for that type of material. Starting from a clean fragment shader, keeping only the normalizations to be do before anything else. First, add a special semantic to the fragment shader. It will be an output only, as a float, and its name is sv_depth. This value will let you write the shaded depth yourself, but only use this when necessary, because that means it won't get rendering pixels that are occluded. Create the coordinates and offset, then go with whatever parallax mapping function you want. Since I explained and wrote this previously, you just need to copy and paste it to the shader. I will use binary search because I like it. Use whatever you find more accurate for your parallax map. After you do this, you can do something to render only whatever area you want. First, convert the coordinates from wall space back to object space, so multiply unity_wall2object by a float 4 with that vector and the w-axis being 1. Then take the perpendicular coordinates of that result. Depending on the mesh up axis, it will be one on another. On Unity, the up axis is y, so if you're using a mesh from Unity, it will be x and z. Blender's default up axis is z, so if you imported that mesh from Blender, it will be x and y. You can now map your Rex mask on these coordinates and discard the pixels. It can be a texture or any function. For example, if the length of these coordinates is lower than 0, it will make the rock circular or an oval depending on the scale of the object. Or if all axes are higher than 0 and lower than 1, it will map a rectangle. Now you cut off the infinite horizon from the rock. What you need to do now is to clip it with the objects that are on top of it. The clip position is calculated by transforming a local position with the model or object to wall matrix, then the view matrix, then the projection matrix. Since we already have the wall position, we can skip that and multiply by the view and projection matrix. Unity has a matrix called unity_matrix_VP that combines both in one. Create a float 4 for the clip position, which is the multiplication between unity_matrix_VP and a float 4 containing the wall position and 1 in the w-axis. One last step that's done for perspective cameras is dividing the clip or screen space position by the depth, because that's how the effect of perspective is done. The sv_depth value will equal the z of the clip position divided by the w of the same clip position, which is the depth in units. Now you finally have a fancy rock shader. The next shader is a type of first shader, but its intention is not to brutally render individual first strands, but to give the effect of fuzziness. While I was working on a render inspired by the coolest guy to ever exist, aside from my dad, and my stepdad, and my bro, and this blog, I focused on the hair system I was rendering for the fur jacket, and I noticed, wait, that's just a volume. Because fur, unlike hair, it's way thinner and more dense, and so instead of drawing the individual hairs as opaque lines, which causes an insane amount of noise, mind you, I could just render a thin volume with some noise to give the effect of fluff. The downside of this is you cannot optimize this to render just the coordinates than the color. You have to render everything together for every iteration, but assuming you're not insane and your number of iterations is around 10 or so, you shouldn't be worried. For that we need the UV coordinates. I want to do some optimizations on the function too. First of all, I want to reduce the environment lighting to a uniform color. That way you don't have to recalculate it every iteration. That is a flow tree where every channel is the w-axis of unity_shar, g and b correspondingly. That is the average lighting, used for tone shaders. First create a flow tree for the main color, a float 2 for the parallax UV with its offset divided by the number of iterations as a float. a float for the directional lighting, plus another float for its intensity, both starting at 0, the phase starting at 0, and finally the delta, which is 1 divided by the number of iterations. After that, create a for loop. Every iteration, you will sample the main texture and the noise texture. You can reuse the high mat slot for that. Add to the resulting color the main texture multiplied by the noise and the delta. Then add to the directional lighting the saturated dot between the parallax normal and underscore wall space light pole 0, plus the noise multiplied by 0.5. That's just an arbitrary value. What it does is shift the dot product to make the effect more noticeable. Then multiply that by the phase, because the lower the phase is, the more likely it is to not receive light. To the directional light intensity, sum the phase. Then sum the coordinates and phase by their deltas, and that should be it for the loop. After it, divide the directional light by its intensity. The final result should be the environment lighting plus the directional light multiplied by its color, which you can get by declaring a float for underscore light color 0. Also make sure you have the forward base tag on your pass. Then multiply this result by the main color. This effect, even if it's more complex than the other parallax mapping functions, it's a nice detail to have if you want your avatar to look fuzzy without turning it into an aliasing nightmare that just had an allergic reaction. Lastly, I want to show you a simple yet cool effect. Recreates the infinite mirror effect with a limited amount of layers. You can do this in any space you want. I will do it in UV space. Create a new function to map the color of the layers. It inputs the current coordinates, then outputs the color of the layer. You can also input the layer number, which will be the iterative variable on the for loop we will create later. So you can do things like a delay on an image sequence or any effect that varies depending on the layer. Create a float to or a float. Create a float to for the offset delta. So the offset vector divided by the iteration count as a float. A float for the phase starting at 0, a float for its delta as 1 divided by the iteration count as a float, and a float tree for the result. Next, create a for loop. This time you will start every iteration by adding the delta to the phase first. Then sample the color of the layer with the coordinates. You can blend the layers in different ways. The simple method is by adding the color multiplied by the phase to the result. You can also blend it with lerp between the result and the color, with the factor being the alpha channel or transparency of the color if it has, or maximum between the 3 channels of the color, or whatever formula you want. That's your choice. That's a nice effect for things like a dance floor on a club or some fancy glasses, although you could also use ray tracing for certain shades, but hey, I'm not complaining as long as you don't use a first shader. Something very important you have to keep in mind is that these shaders are still heavier than the standard shader. So keep your iteration count around 10 or 16, doesn't matter if it runs well on your editor window. Anyways, I talked too much for today. I hope you have fun making your cool parallax shaders or your cool whatever shaders. And yeah, that's all. Oh, by the way, I have a Discord server. It is very tiny. It is tiny, but it's my Discord server. So it's not only for YouTube, but for my stuff, my Gumroad stuff, my Twitter renders. Like, it's for anything in general. So if you want to join, it's on my description and it's on my YouTube profile. So yeah, goodbye.